Welcome back, everybody, for the third talk of our session today. This is going to be by Ryoya Arimoto, and we're going to hear about topological full groups arising from Cuntz Toeplitz algebras. Take it away, please.
Thank you. Thank you very much for introduction. And I'd like to thank the organizers for giving me the opportunity of the talk. I'd like to talk about topological figures arising from Kuntz-Toeplitz algebra. First of all, I'm operator algebraist, and I'm interested in the operator algebra constructed from groups or group actions. And this is the part of the joint work with Taro Sogabe, who is also operator algebraist. And this is a part of joint work because the other result is purely operator algebraic. And rather, it is the main result of our work, but I will only talk about the result, which includes the geometric group theoretic frameworks. Okay, so let us start with fixing notations. Let n be integers greater than 2, and Tn denotes the rooted and regular tree like this. This is the picture of T3. So it is rooted, and each vertex has 3 children, right? And the vertex of the tree, the set of the vertex of the tree can be identified with the finite words on n letters. For instance, this vertex can be described as 1, 2, 3, so 2, 1. And V0 corresponds to the root, right? And del of Tn denotes the boundary of the tree. I mean, this is the set of all infinite passes in the tree starting from the root. So this space can be identified with the infinite passes or infinite passes on n letters. Okay, and the Tn bar denotes the complexification of the tree, meaning that it's the union of the tree and their boundary. As the name suggests, it is compact host of space, but we don't use it today, right? And for each vertex in the tree, say mu, we define z mu as a vertex, the set of vertices. They are below mu. Okay, so this is the subtree of the tree. And del z mu denotes the corresponding, actually this is a closed set of the boundary, but the corresponding set in the boundary of the tree. And finally, z mu bar denotes the compactification of the z mu, right? Okay, this is the notation. And so the group we will consider today is based on the Higman Thompson group, which is a generalization of the Thompson group V. So let us recall the definition of the Higman Thompson group. Let mu's and nu's in the vertex of the tree, such that they spans the boundary of the tree, meaning that each element in the boundary of the tree, there are some I, but that element starts with mu I, right? And same for nu's. Then the replacement of mu j with mu j. So each element of the boundary can be expressed as mu j blah blah blah. So replacement of mu j's with mu j for some j defines a homeomorphism on the boundary. And this map is denoted by this. Okay. For instance, if we choose mu's as this, so here's mu1, mu2, mu3, mu4, and mu5, and we choose mu1, mu2, mu3, mu4, mu5 like this, then this defines the homeomorphism of the boundary. So boundary in here moves to here. All right. Then the Vn is defined as a collection of such homeomorphisms. So a collection of such homeomorphisms forms a group, and this is said to be a Higman Thompson group, Vn. All right. If n is even, this group known to be simple. And if n is odd, then the group itself is not simple, but its combinator subgroup is simple. And its abelianization, meaning that this is a quotient of a group by abelianization of the group. Sorry, the commutative subgroup of the group. And abelianization is isomorphic to Z over 2D. Okay. And it is known that this group has a deep relationship between the Cuntz algebras, one of the most important operator algebra. So let us introduce the Cuntz algebra. First of all, the cyst algebra, which is the main research object in the operator algebra theory, is roughly it is a C algebra with norm and state operation, like matrix, like matrices. It has a norm as a operator norm, and it has a joint as a state operation. I mean, the transposing and taking a complex conjugate. Then ON is defined as a universal cyst algebra. It is it may be confusing for those who are not familiar with operator algebras, but yeah, this is a universal cyst algebra generated by n elements S1 to Sn, satisfying this relation. This is called Cuntz algebra, and this is one of the most important operator algebra. So those who are not familiar with operator algebra, one can think that a Cuntz algebra is just a star algebra generated by S's with this relation. So today you don't have to consider about norms. And it is easy to take that this algebra is spanned by the elements of this form. Here, for mu, for finite word on n levels, mu, this set is identified with the subset of the trees. So for vertex of the tree mu, S mu denotes S mu1, the product of S mu1, S mu2, blah blah blah, S mu n. So each mu i's are in from 1 to n. Then this is the one of the generators, and this is the product of generator. And this denotes the length of mu. All right, and it is not hard to see that Cuntz algebra is generated by or spanned by element of this form. Okay. And here, this is a distinguished subalgebra of Cuntz algebra, spanned by the. So in the Kuntz algebra, mu and nu can be varied, but for the n, this is equal. Okay, and it is shown to be commutative subalgebra of ON, and it is isomorphic to continuous functions on the boundary of the tree with this identification. Right? And U of ON denotes the set of unitary elements. Unitary means that the element satisfying this relation, and U of ON denotes the set of unitary elements of ON, or unitary elements of Kuntz algebra. And here is a deep relation between the Higman-Thompson group and Kuntz algebra. First, Nekrasovich observed that there is a nice group homomorphism from Kuntz algebra to from Higman-Thompson group to a Kuntz algebra. So this is a concrete form of the element of Higman-Thompson group. This is sent to this form of element. This is a group homomorphism from Vn to unitary elements of the Kuntz algebra. And later, further up, I'll show that the range of this group homomorphism generates the Kuntz algebra, meaning that the smallest sister subalgebra containing the range of this homomorphism is the whole Kuntz algebra. This means that this group homomorphism is kind of surjective. All right. And we can see the relation clearly through groupoids. Here, groupoids, the precise definition of groupoids is, of course, the small category whose arrows are all invertible. But in the operator algebra setting, we consider groupoids as generalization of course, groups and group actions. Of course, groupoids is groups with many units, and the arrows in groupoids, we may think that arrows in groupoids represents dynamics from a domain point to range point. It is very local dynamic, meaning that we only consider domain points to range point, not globally. Right? Then from groupoids, we can construct many objects, including sister algebras and groups. From a groupoid, we can construct groupoid sister algebra. And we can also construct a topological full group, which is a discrete group constructed from groupoid. And this represents the global dynamics of the groupoid. So it's gluing, it is constructed as gluing local dynamics of the groupoid. Okay. And right. And there is a nice groupoid such that its groupoid sister algebra is a Kuntz algebra, and its topological full group is Higman-Thompson group. From this, you can see that Kuntz algebras and Higman-Thompson group have a deep relationship. Okay. And we can also construct the Higman-Thompson group directly from Kuntz algebra, like this. These two matrices. Okay. This is a picture representing a relation between the Higman-Thompson group and Kuntz algebra. So here's a groupoid. And from a groupoid, we can construct a Kuntz algebra. And also, from a groupoid, we can construct a Higman-Thompson group. And we can directly construct Vn from On and vice versa. And we can recover a groupoid from Higman-Thompson group. Precisely recover from the action of the Higman-Thompson group on the control set. Also, we can recover a groupoid from Kuntz algebra. Okay. Now, we will consider the generalization of the Higman-Thompson group. So in operator algebra, the Kuntz-Toeplitz algebra is known, which is some generalization or relevant of the Kuntz algebra. Here is the definition. The Kuntz-Toeplitz algebra is defined as a universal cyst algebra generated by T1, T2, blah, 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 Tn with this relation. Comparing to the Kuntz algebra, the condition is more relaxed since the Kuntz-Toeplitz algebra doesn't have this relation. Right? So it has a map from the Kuntz-Toeplitz algebra to Kuntz algebra, sending the genders Ti to Si, like this. Its kernel can be computed, and it is the algebra of compact operators. Okay, so this is a relevant of the Kuntz algebra. And like we can construct a Higman-Thompson group of the Kuntz algebra, we can construct a new group from this algebra. We say here it gamma n. Okay, and we also have a groupoid such that its groupoid sister algebra is Kuntz-Toeplitz algebra, and its full group, topological full group is gamma n. Okay, and natural question is that which space gamma n naturally acts on? So in both operator algebra and geometric group theory, the nice properties of Higman-Thompson groups can be deduced from the action of the group on the control set. So to analyze this group, it is happier if it admits a nice action. And it is nice if we can describe the action concretely. And finally, what is the property of this group? This is the natural questions for this new group. So this is some conceptual definition for you. So let us give you a concrete definition of the new group. Let mu's and v's and the nu's and w's vertex or a tree, so rooted and regular tree, such that in addition to they span the boundary of the tree, but they also spans inside of the tree. I will show you the picture later, but they generate whole of the compactification of the tree, and same for nu and w. And if we define a map like send mu I omega to nu I omega and vj to wj, then it defines the homeomorphism of the compactification of the tree. And gamma n is defined to be a collection of such homeomorphisms. Let us show you the example of the elements. Here is a mu1, mu2, mu3, mu4, and mu5, and v1, v2, v3, v, and v4. And they span the whole of the tree, meaning that each vertex is either starts from some mu or it is some v. All right, and it is same for news and w. Then the map defining so this sending this subtree to this subtree and this subtree to this subtree like that, and v1 to sending v1 to w1 and v2 to w2 like that. So Higman Thompson group only consider the dynamics on the boundary of the tree, the Cantor set. But in this group, we consider the dynamics of the compactification of the tree. So including the inside of the tree, right? Finally, we see the properties of the gamma. So it has a nice normal subgroup, say lambda n. This is the group of finitely supported permutations of the vertex of the tree. So since the elements in lambda n is finitely supported, so they do nothing around the boundary of the tree. So it is normal subgroup of gamma n, and its quotient represents the dynamics of element of gamma n of the boundary on the boundary. So the quotient is isomorphic to the Higman Thompson group. This is like Cuntz algebra is represented as a quotient of the Cuntz-Toeplitz algebra by compact operator. Okay, and our main result shows that structure of normal subgroups of this group and abelianization of this group. First, the normal subgroup of gamma is as this. So trivial one and commutative subgroup of gamma n, and this nice normal subgroup and commutative subgroup of this group. Right. And abelianization of gamma n is computed as 0/2z. This is independent of n. So in the Higman Thompson group case, abelianization varies on n, but in case of this group, it is independent of n. And abelianization can be computed as this map. Here, these inclusions defined as follows. So in gamma 3 or T3, there's a movement over the vertex of the tree. So this vertex may go another place. We encode this movement into V5 as the adding new edges into gap of original edges. And then we can obtain the inclusion map from gamma n to V to n minus 1. Okay, so this is the end of my talk. So thank you for listening.
Thank you very much, Ryoya. Are there any questions for the speaker?
I have one question.
Mhm.
Are you able to give any finiteness properties, and does it have some, maybe it's not F infinity or something like that?
I don't know much about that. Even I don't know it is finitely generated.
Oh,
I haven't confirmed it precisely yet, but I believe that this is finite generated, but I haven't confirmed yet.
okay.
Yeah. So it includes the S infinity. So a group of finitely supported permutations.
Yeah.
So we don't know. Yeah. We don't know directly that it is finitely generated or not.
Mm. Thanks.
Thank you,
Thank you.
Murray. Are there any other questions? Looks like not, so we'll thank Ryoya again. Thank you for the talk.